In this video, we're going to be talking about our particle models of bond energy and thermal energy. To do that, we're going to start by using an analogy of a spring. The reason that this is useful is that particles in bonds tend to vibrate back and forth, increasing and decreasing their separation ever so slightly. We're interested in understanding how much of this energy is in kinetic energy and how much of this energy is in potential energy. This graph represents the potential energy and kinetic energy of a spring. The x-axis is the distance from equilibrium. It's how far the spring has been expanded or compressed. The y-axis is the energy. This right-side-up parabola represents the potential energy, while this upside-down parabola represents the kinetic energy. Let's make sure that we're clear about what this graph represents. We know that the potential energy of a spring is at its maximum when the spring has been expanded to its maximum length, or compressed to its minimum length. This is represented by the fact that the potential energy gets large as we move away from the equilibrium. Also, when the spring is stretched to its maximum length, or compressed to its minimum length, it stops moving for a moment. This is why the kinetic energy is zero at these far points. When there's no potential energy, in other words, when the spring is at its equilibrium distance, the kinetic energy is at its maximum. Let's ask a question. What are the average kinetic and potential energies for the spring? By average, we mean an average in time. Potential energy and kinetic energy are constantly trading places. Let's just think about what happens in one oscillation. One full oscillation means the spring starts at its minimum length, expands to its maximum length, and then goes back to its minimum length. During this time, it passes through its equilibrium position twice. So we have two moments where the spring's kinetic energy is at a maximum and its potential energy is at a minimum, and two moments where the potential energy is at a maximum and the kinetic energy is at a minimum. We're not going to calculate it here, but it turns out that the average amount of energy in each of these energy systems is 1/2 of the total energy of the spring. Remember, this is just an average. This does not mean that the kinetic energy is always 1/2 of the total energy, or that the potential energy is always 1/2 of the total energy. It just means that on average, they're 1/2 of the total energy. We can use this model with bonds as well. If we have a system of particles that are bonded with no thermal energy at all, the particles will just sit at the equilibrium distance apart. If we start adding thermal energy, the particles will start to wiggle. On average, half of the energy that we add as thermal energy will go into the kinetic energy of the particles, and half of that will go into the potential energy of the particles. Now you may be thinking, wait, I thought the potential energy of the particles was the bond energy. The bond energy is equal to the amount of potential energy that the particles have if they have no thermal energy. But if we add thermal energy, the potential energy of the particles changes. However, the bond energy itself does not start changing until the particles undergo a phase change. You might have thought that when we added 2 × 10⁻21 joules of kinetic energy, that 2 × 10⁻21 joules would stay as kinetic energy. However, your data should show you that this is not the case. Only half of that energy ends up in the kinetic energy. The other half ends up in the potential energy of the particles. So let's take a moment to see how we can write this down. We want to know how we can relate bond energy and thermal energy to kinetic energy and potential energy. We'll start with kinetic energy because it's the simplest. The kinetic energy only comes from thermal energy. There's no bond energy that's associated with the particles wiggling. But we know that only half of the energy that we add as thermal energy actually ends up in the kinetic energy. Writing this mathematically looks like this. Next, we want to think about the potential energy. Well, one thing we know for sure that's in potential energy is the bond energy. But what else ends up in potential energy? we already know that it's 1/2 of the thermal energy. Notice what happens if we add these two equations together. We get kinetic energy plus potential energy is equal to E bond plus E thermal. These are just two different ways of describing the same thing, the total energies of the particles. The total energy is equal to the kinetic energy plus the potential energy, or alternatively, it's equal to the bond energy plus the thermal energy. So how does this energy get divided up amongst all the individual particles? It probably doesn't surprise you that this energy gets divvied up evenly amongst all the particles. Imagine if we had a chunk of particles with a certain amount of energy, and then we added some thermal energy to the particles. But instead of distributing itself around the system, it ended up just going into a single particle, causing that particle to vibrate back and forth very rapidly. That would be a little bit strange. And even if this did happen, that energy would quickly end up being distributed to the particles around it. So we expect that on average, every particle should get the same amount of thermal energy. For example, if we had 1 joule of thermal energy to add to a system, and that system had Avogadro's number of particles, how much energy would each particle get? Well, it would just be the 1 joule, the total amount of energy, divided by the number of particles. There's one subtlety that we haven't talked about yet. Can you see a problem with these two expressions that might crop up for certain substances in certain phases? Think about a gas. We've said that a gas is just a bunch of particles that are not bonded together. So by definition, a gas has no bond energy. There are no bonds between the particles. So this expression doesn't make sense for gases. It only works for solids and liquids. So what does this then become for a gas? Well, in the case of the gas, potential energy is just 0. There's no interactions between the particles. This just means that all thermal energy can be found in the kinetic energy of the particles. We now have a model for both thermal energy and bond energy that depends on the behavior of the particles themselves. But we're not quite where we want to be. We now want to make a connection between thermal energy and temperature. We know that thermal energy is related to the temperature of the object, but not exactly how yet. In the next DL, we're going to start to extend this model to include an explanation for how this works.